Good evening. I think we had started quantification of fluorescence in the last class. I had indicated to you that if we take a look at the relationship between fluorescent power and the number of molecules which can be excited, then we can derive a relationship similar to Beer-Lambert's law. This we had seen earlier in our last class, and then what we had done was we defined radiant power of the fluorescence as a function of fluorescence efficiency or quantum field, and the difference between the amount of radiation that is absorbed or that is absorbed. So, the fluorescence efficiency, we described it as the ratio of the number of photons emitted as fluorescence to the number of photons absorbed. So, obviously we can write an expression something like this, that is Pf is equal to Qf and then a second constant K2 and then P naught minus P. So, put all this together, Qf and K2, we can write K dash or K1 into P naught minus P. Beer's law is something similar to this, P by P naught is equal to 10 to the power of minus epsilon Bc, where epsilon is the molar absorptivity. Since both the quantities are similar, what we derived was we substitute equation 3 in equation 2, that is P naught minus P in that equation. So, what we wrote is fluorescence is a function of P naught into the power of 1 minus 10 to the power of minus epsilon Bc. This is absorbance basically. So, the exponential can be expanded in that bracket something like this, and then we have neglected the longer terms and then retained the first term, that is 2.303 into the power of epsilon Bc, and once epsilon Bc square etc., epsilon being the very small, we neglect that, and this 1 and 1 will cancel. What remains is 2.303 epsilon Bc, all square terms will go. This indicates the, here again if fluorescence is a function of P naught, this is a constant, 2.303 is a constant, K dash is constant, molar extinction coefficient is constant, and B is path length is constant, we can keep it. P naught is the initial radiation, that is constant. So, F is proportional to C, that is what we can write. And at higher concentrations what happens? At higher concentrations the equation becomes definitely non-linear and reaches a value of P naught minus P naught Qf. So, that means all these terms will can be replaced as P naught, Pf is equal to P naught and Qf, and replaced as Qf asymptotically where there is no dependence on concentration. See, this is very important difference between absorbance and fluorescence. What we are saying is at higher concentrations fluorescence is so high that it ceases to be a function of the concentration. Therefore, essentially fluorescence is a function which is concentration dependent only at lower concentrations. At higher concentrations it reaches a saturation value, and once the saturation value is reached you cannot correlate it to concentration. Why this happens? So, it is a very interesting function, because if you imagine we have an incoming radiation and here is the fluorescing material in this cuvette. What happens is the fluorescing molecules will be concentrating only in this area. So, most of the radiation is absorbed by a layer of molecules present here, and then the molecules present in this side will be starved of incoming radiation. So, what happens is maximum fluorescence is obtained only in the left region. Therefore, if you take a look, after that whatever is the concentration of the fluorescing materials on the outside this circle what I have drawn here will become useless, because they will not contribute to the fluorescence at all. So, it is important to have the distribution of the molecules distribution of fluorescing molecules should be very dilute and uniform. Uniform throughout the sample. If this is not so, then we have the problem of fluorescence concentrating only near the junction where the P naught and the cuvette molecules are located, and the molecules located behind it are starved. So, this is what I was trying to tell you. Then we have derived a relation something like this, and this is how as it asymptotically reaches as concentration becomes more, F will become P naught will be equal to P. However, this holds true only if epsilon Bc is small, otherwise it is it holds true only for dilute solutions. At higher concentrations what happens is the relationship between fluorescent power and concentration becomes non-linear and reaches a value of P naught into Qf asymptotically. So, there is no dependence on concentration. Moreover, the detector being at a perpendicular position to the incoming radiation, it receives only a very small portion of the fluorescence emission depending upon the solid angle. So, we are not going to measure the total fluorescence when the radiation is coming from one side. We are measuring the fluorescence starting which is facing near the incoming radiation, and total fluorescence we are not measuring because we are not placing the detector on the other side of the cuvette. We are placing a detector at the bottom. That means the radiation will come like this, and then since fluorescence occurs in all directions, I can place the detector at the bottom so that only the fluorescing radiation comes through, but the absorbing radiation is automatically cut off. This is one of the fundamental principles of fluorescence. That means essentially we are measuring a small solid angle through which fluorescence is coming through, not the total fluorescence. Suppose I keep the aperture very small, a small amount of fluorescence will reach the detector. Suppose I make the aperture slightly bigger, more amount will reach the detector, more amount of radiation, that is fluorescing radiation. So, the fluorescing radiation is actually dependent not upon the sample per se, but it is also dependent upon the solid angle through which we are measuring. This is a great difference between fluorescence and absorbance. So, if I keep the measuring angle bigger, for the same concentration I can get a higher fluorescence reading. So, there is no limit, there is no lower limit through which I can say this fluorescence procedure is applicable to only this concentration. and I cannot say this is the absorbance reading, this is the epsilon value for the fluorescing molecule. Why? Because I can open the detector angle, solid angle, collect more fluorescence, I can always say linearity changes. This is a very important aspect of fluorescence. So, the efficiency of the detector again is the deciding factor of how much fluorescing molecule can be detected. So, it depends upon the fluorescing wavelength also, and the equation phi can be modified into this form now, that is 2.303 P naught into P naught is incident radiation, F phi is the efficiency, and G lambda is, it depends upon the wavelength weight factor, and QF is the quantum efficiency, and again epsilon BC will remain as such. So, again all these things can be converted into another constant except C. So, this K represents the product of all these numbers, and B is the path length that will remain constant. Okay. So, a plot of fluorescence versus concentration should be a straight line. So, this is something similar to Beer-Lambert's law now. So, normally linearity in fluorescence occurs 2 to 3 orders of magnitude, that is because I can always extend the solid angle through which I can collect the fluorescence. So, in absorbance when I make a calibration curve like this and then I get a calibration, I get linear relationship between 1 ppm, 2 ppm, 3 ppm, 5 ppm, but of the same order, maybe one order more, 1 ppm, 10 ppm, then above 10 ppm Beer-Lambert's law will not hold good. So, if it is up to linearity is up to 150 ppm, then I can measure in 10 ppm, 20 ppm like that, 10, 50, 75 like that. But in fluorescence I can measure 3 or 4 orders of differences. For example, in the figure what I am showing you in the next slide will show you that this linearity, this extends from 10 raised to minus 6 molar and 10 raised to minus 5 molar, 10 raised to minus 4 molar, and maybe up to 10 raised to 2 into 10 raised to minus 4 or something like that, but definitely 10 raised not 10 raised to minus 3 molar. That means the linearity varies from 10 raised to minus 6 to 10 raised to minus 4, that is 1000 times, this is 100 times, this is 10, and then 10 raised to minus 4 is 100, and then sometimes if you are lucky it may go up to 10 raised to minus 3, but rarely the fluorescence will be linear in the higher regions. So, but still this itself is a great advance for the detection of materials, especially fluorescing materials, because the application of this principle would permit you to work at higher ranges and different ranges also. So, this equation, that equation 7, no, that is what we had this equation, F is equal to F K B C, or all this to put together, that equation is interesting from 2 aspects. One is it shows that sensitivity can be increased by working at high excitation power. Again we go back to the equation, see F is proportional to P naught also, and higher the incident radiation, more would be the fluorescence, and Fi, this is the fluorescence efficiency. So, more high input power, more is the fluorescence efficiency. So, that is one aspect, and the second aspect is it gives a large signal to noise ratio. Since the square of intensity can change from time to time, source intensity can change from time to time, fluorescent signals cannot be measured in absolute parameters. This I have already told you, taking an example of solid angle. So, in solid angle what happens is for the same concentration I can get a higher reading by opening the slit of the detector more, or lower reading by reducing the slit for the detection. Therefore, they are all fluorescence data are expressed as relative fluorescence. Therefore, all fluorescence measurements normally are made relative to some reference standard of known concentration and corrected for background fluorescence and also for the fixed slit width. If you remember this, you will be mastering the fluorescence methods. So, what all you have to control? You have to control the incoming intensity, that should be as high as possible, and number 2, the solid angle can be increased much more, and then the concentration also can be changed to different molar ranges. So, another interesting feature of equation 7 is the freedom to adjust the slit width. Therefore, there is no absolute fluorescence for any of this thing nowadays, even though nowadays you can, there are couple of instruments where you can present the absolute fluorescence, but it is not actually absolute fluorescence at all. There will be some amount of you cannot measure 100%, there will be some amount of difference, and in actuality the term B does not refer to the path length of the cell at all, but it is the solid volume of the beam that reaches the sample together with the emission slit width and the beam geometry. Therefore, all slit widths are critical factors in fluorescence instead of the actual cell dimensions. So, this is a very important aspect. So, if I show you the figure for fluorescence, you can imagine how it is coming out like this. Now, I have a slit here, my sample is here and another slit is here. So, my radiation is coming through this slit into the cell, this is the solid angle. I place a detector perpendicular to this, I do not keep a detector across that. So, emission light is always perpendicular to the incoming radiation. So, this is known as excitation light beam, this is known as emission light beam, and again I need a slit width. So, this the excitation light beam slit should be as large as possible, and here the slit also should be variable. So, the same thing, same geometry I can show you in different format, but the essentiality is that the collection of the fluorescence intensity is at right angles to this incoming radiation. So, these are the different observation angles. I can place a detector at the bottom also, like I was telling you, but if the analyte is too concentrated, the fluorescence versus concentration reaches a maximum and falls off. So, this I have shown you earlier, here it reaches a maximum and falls off, because afterwards there is not enough radiation to reach the molecules. So, this behavior can be attributed to the attenuation of the exciting radiation, as I already told you, and this results in a further decrease in the excitation power. Therefore, same fluorescence reading can indicate two different concentrations. You should have understand this aspect. Suppose I measure a fluorescence intensity of somewhere here, there is also another one, another concentration which is on the straight line range. So, this we do not know what is the concentration here. When I measure an unknown, I do not know whether I am in this range or in the linear range. So, for any fluorescence there could be two concentration ranges indicated as a solution. So, one has to be a little careful which region we are really operating. So, another phenomena occurs in highly concentrated solution, that is excited molecule may form a complex with another ground molecule, that causes a bathochromic shift. This phenomenon is known as self quenching and the complex is called an excimer. So, dilution sometimes it helps to reduce this effect to some extent, because the excimer concentration varies as the square of the solute concentration. So, here I am showing you the excitation and emission spectra of the phenanthrene compound. This is a aromatic 3 fused aromatic rings fused at ortho positions, ortho and para positions, and the excitation spectrum I am plotted only relative intensity versus wavelength. Here you can see that the excitation wavelength is somewhere near 250 or something like that. Okay. There is one excitation wavelength here somewhere around 220, but 250 seems to be a slightly better more sensitive, and the emission spectrum starts not from 300 or immediately thereabouts, but from about 350, 325, 330 or something, and the excitation spectrum has got a maximum somewhere around 350, and then you can see that there is one more on the around 460 or something, another at 500. Then there are other small peaks which are this thing. Therefore, what is important in this case to note is both the excitation and emission are approximately similar in shape. You can see E and F, and P of course there is a slight difference, but E and F they are approximately similar only. So, a fluorescing compound is associated with 3 types of photoluminescence spectra. The first step involves the generation of absorption spectrum. First you should material should be having capability to absorb the radiation. That means it must have an absorption spectrum, and then if there is an absorption spectrum, the compound can be a fluorescing compound or it need not be. But if there is no absorption spectrum, the compound need not be fluorescing at all, that follows. So, the second point is, if the compound is capable of absorbing, then excitation spectrum is essentially identical to an absorption spectrum also. So, there will be some similarity, and emission also will be somewhat similar, but at a different wavelength. So, fluorescence spectrum obtained by measuring the luminescence intensity at a fixed wavelength, you can choose the excitation wavelength for different measurements, concentrations. See, for example, in the previous slide I had shown you that while excitation remains the same at 250, I can choose either 350 or 425 or something like that, 460 and somewhere around 500. I can choose any of these 3 for my fluorescence measurement, but excitation remains the same, that you cannot change. So, once excitation wavelength is fixed, then I can determine the emission, fluorescence or phosphorescence spectra by recording the emission intensity as a function of wavelength. So, whenever you want to optimize a fluorescence method, what you should do is you must record the fluorescence highest where the excitation wavelength is fixed, and using that excitation wavelength, fixed excitation wavelength, you should measure the emission wavelength. So, again there are different factors which can be tested to optimize a procedure. So, normally what we say is fluorescence and phosphorescence bands are generally found at longer wavelengths. This I have already told you. The wavelength of difference between the two provides a convenient tool to measure the energy difference between the singlet and triplet states. This is also somewhat understood by now, because phosphorescence would be through the triplet state. In true spectrophlorimeters, excitation spectrum as well as fluorescence emission can be obtained. So, both these can be obtained in a good spectrophotometer, spectrophlorometer we call it. The excitation spectrum can be obtained by measuring the emission at some fixed wavelength. It can be arbitrary, but whenever you get maximum emission, the corresponding excitation is gets automatically fixed. So, that wavelength will be the excitation wavelength, and when we are scanning excitation, and once the correction is made for excitation along with source output intensity and detector response as a function of wavelength, an absolute excitation spectrum also can be obtained, which closely resembles an absorption spectrum. So, this I have a point I have already conveyed to you. Then what we do? We fix the excitation wavelength and then scan the emission wavelength now. That can be obtained by fixing the optimum excitation wavelength and scan the detector response at higher wavelengths, not lower wavelengths. So, once both these are fixed, excitation and emission spectra are approximately mirror images of each other. This point I have already conveyed to you. So, the vibrational energy difference for the ground and excited states are essentially the same. That is why the spectra also look approximately similar. See for example, here in this figure you can see that the fluorescence intensity is plotted against emission wavelength. So, A is excitation wavelength. See here, this figure is essentially similar to, as if this figure is pushed to the right almost. See, these two peaks correspond to these two, and these two have vanished here, and then there is one more appearing here. So, still you can say that both of them are approximately similar only. This proves the point what I was trying to teach you earlier. And now, having learned so much about the fluorescence, we can look at the instrumentation in a fairly quick manner. What we need basically is a source of light, and then what I need is a monochromator or a filter, and then this one I need to choose the excitation wavelength. So, then I have a sample cell here, and the job of this monochromator is to provide the wavelength suitable for excitation to the sample, and then I place a monochromator on the at right angles to the incoming excitation beam, and then I put a detector, and then I connect it to a electronics recorder, etc., and then I can also have some sort of a beam attenuator to account for differences in the intensity of the source during measurement. So, that is a part of the electronics, but if it is there in place, then what I can do is, what I can say is, whatever changes happen in the source are automatically corrected during measurements or throughout the experiment. So, basically the instrumentation is a very simple this thing, and then it needs two monochromators, and sample cell and beam attenuator and computer and other things as depending upon the this thing, but we also need a detector. The most of the things what we have learnt earlier with respect to instrumentation are all there in this system also. So, there is no need for us to go into details of this except for some small minor changes. So, now let us look at the radiation sources. So, what are the radiation sources for this? We can choose a high pressure xenon arc lamp. These are nothing very special. If you are going to a marriage or somewhere, you would have seen that there is a guy who shoots the video pictures, he uses high pressure xenon lamp. Okay. And nowadays most of the cars also, whenever they are traveling on highways etc., are fitted with xenon lamps, and the specific technical specification includes about 75 to 450 watts is required. This gives very intense radiation and gives a relatively stable output. Higher the wattage, the output will not be stable. Okay. So, the power supply should be between 5 to 20 angstroms at about 15 to 30 volts. So, this output approximates that of a black body and continuum output from 300 to 1300 nanometers. That means, using a xenon arc lamp you can have an excitation wavelength from 300 to 1300 nanometers and emission also. So, it is normally it is pulsed to obtain higher peak intensity. AC signals from the transducers can be amplified and processed, therefore, we convert from DC to AC. So, there is approximately about 1% drift per hour and limited by the arc wander and electrode wear. Normally instead of arc you can use normal xenon lamps also. Nowadays there are a lot of xenon lamps which give you steady output, but their life will be slightly lower because the temperature of the xenon radiation source could become very high. Therefore, it is essential in the instrumentation for the xenon lamp to be covered with a cooling tower and cooling water circulation. So, we can also choose a xenon flash lamp, and essentially it is a charged capacitor discharged through a lamp filled with xenon, and we can have an image about 2 mm wide and 18 mm height. It is very useful for microcell and continuous flow measurements. This advantage of this is it is of low cost and compact source. You can also have blue light emitting LEDs as a source, and they are not much in use as a routine instrument, but they are there around. You can use hydrogen lamp also for excitation, but again the hydrogen lamp could also cause decomposition of the sample. So, low pressure mercury vapor lamp is another one. This is not so good as a xenon lamp. The mercury vapor lamps you must have seen all over, they are coated with a phosphor that emit a nearly continuum spectrum, but they may also be used with a clear bulb of quartz. If they can encase that in a quartz bulb, you can generate very intense lights corresponding to 253.7 nanometer and 313 nanometers and 404 nanometers, 407.8, and these are all I have indicated the strengths of the lines, excitation lines. For example, 253.7 is very strong, 313 is medium, 365 and 404 is they are medium strength, and 407 is a fairly weak, but 435.8 is a strong radiation. It also give you another 3 radiations, that is 546, 577, 579.1 nanometers. So, what does this tell you? basically mercury vapor lamps give a continuum spectrum, but in the continuum spectrum you will see very strong lights corresponding to these wavelengths, that is 253.7, 313, 365, 404, 407.8, 435, like that you can see. The point to be noted here is that most of these lines can be separated from each other by using simple filters. Okay. So, I can use mercury vapor lamp as a low end substituent, low end spectrophlorimeters with filters instead of monochromators. If I use a xenon lamp, I have to use a monochromator to get plus or minus 0.2 nanometer accuracy, whereas in this case in mercury vapor lamps I can go for filters. So, filters are cheaper compared to monochromators, lenses, monochromators, mirrors and all those things are avoided if I use a filter. So, the other details are for you to remember is mercury vapor pressure in the lamp is approximately 10 torrs and arc discharge lamp emit very diffuse radiation. So, it is not so good, but high pressure arc lamps are better, and we need to use interference filters that are used to select individual mercury lines of 253, 313 etc. all these things. So, many filters are available if you use mercury vapor lamp. Okay. Now, that is another part. Third part is if you can use a laser. Lasers are also used, Nd:YAG or any other fixed wavelength lasers can be used if the wavelength of the excitation matches the fluorescence excitation wavelength, otherwise they are very difficult. But nowadays you also get tunable lasers. With tunable lasers again it should be possible for us to get very high intensity, but again compared to xenon arc the mercury filter will be less costly, but tunable laser would be of very high cost. So, again there is a need for justification of the lamps depending upon your work. So, if we talk about optics, what we can say is a normal filter photometer usually employs a mercury lamp as an excitation source. Therefore, primary filter is required like an interference filter, and then through the optical cell another filter is known as secondary filter is required to transmit the fluorescence radiation onto the detector. So, the secondary filter also serves to absorb the scattered excitation radiation belonging to other wavelengths. So, that permits only the emission wavelength. So, excitation filters are normally bandpass filters that transmit a comparatively broadband of radiation as against a single mercury line. So, emission filters are usually of cutoff type. So, with which pass long wavelengths and attenuate shorter wavelengths. So, bandpass filters have more than one transmission windows. If you look at the discussion what we had during optics, you will get all this once again, that is why I am not going into details of this. So, if glass filters are used, they frequently fluoresce themselves, that itself can be a little bit of a nuisance, and stray radiation is more whenever you use glass filters. So, filter photometer optics cannot resolve Rayleigh and Raman scatter peaks, that is understood. So, if you want to resolve Rayleigh and Raman scatter, then you need to go for xenon arc or Nd:YAG laser. So, grating monochromators, they are used in place of excitation filters that permits 200 to 800 nanometer, that is where you get maximum fluorescence for most of the organic compounds, and then sometimes distortion also occurs whenever gratings are employed. These things we will have to be very careful whenever we are using this thing. So, gratings normally of 600 grooves per mm blaze for 300 nanometer are used for excitation. Focal length etc. are all matter of details that corresponds to 0.254 meter, and f by 4 and f by 5 apertures are used. Filters are used to block higher radiation, and excitation and emission should be able to resolve normally of about 1.0 nanometer wavelength, that is the ultimate. So, we will talk about the cells and compartments. We will discuss about this after a small gap. So, thank you very much. We will continue our discussion on the instrumentation of fluorescence shortly.